Now we're going to go through the process of checking your stray light, what we call under dry conditions. This is an initial check that all ELSD users should do. So here's the first step. We're going to turn the unit on. Okay. It's coming up, it's booting up. Just take a few seconds here to get to the operational screen. We set the temperature to 50 degrees Celsius and the gain to 12. You want to set the gain to 12 because that's maximum sensitivity for the ELSD. We crank that stray light. We have gas pressure at 3.5 bar. The temperature is blinking because it's coming up to temperature at 50. Signals at 101 millivolts. We're going to turn the LED off, auto zero the detector, turn the LED back on. This is on a SETX 85, and you're looking at this stray light level. On top of that, you want to add a plug to the liquid inlet here on the left. You want to make sure you put a plug on this to prevent any atmospheric air from getting in there, because believe it or not, from the Venturi effect, it'll add noise to the baseline with just the air coming in that small hole. Also, you want to make sure you have liquid in the gooseneck, the liquid trap. Plug the liquid line, put liquid in the trap, units at gain 12, 50 degrees C, 3.5 bar of gas. I'm using compressed air that's running through a desiccant trap, but you might be using nitrogen. And right now, this unit has 100 millivolts of stray light. So what we're looking to see is that the baseline is stable at gain 12, gas only. And this is a perfect example. And you can see the baseline is stable because it's only reading 100 millivolts and it's not bouncing. So if it was bouncing between 98 and 102, I would say you have a noise issue or a contamination issue. You want to make sure your stray light is stable with gas and at gain 12 with the light on. And we're going to go over to the chart. Now we're going to look at the turbidity chart for ELSD. We've already turned the unit on, we have it running, it's equilibrated, and it's up and humming. Now, the turbidity chart represents things that add to your dynamic range consumption. In other words, the unit has a 0 to 1,000 millivolt full-scale response capability. When the unit is off, it's obviously at 0 millivolts. That's where we started. We turn the unit on, you come up maybe to 2 millivolts. Then you turn the light on, which we just did, the stray light, and we're at 100 millivolts right here. And we're looking at noise that's less than 2 millivolts. So we've established that the unit electronically is okay, and the unit is running with gas and is quiet. There's no random spiking. The next step we're going to do is we're going to turn on the solvent. And this is going to be pure water. And we're going to see another step increase in turbidity. And it's critical to think of turbidity as something that consumes your dynamic range, because the unit has 100 millivolts stray light. There's nothing you can do about it with perfectly clear gas. When you turn on your mobile phase, you're going to have another increase. And your mobile phase could be water, it could be organic mobile phase with buffers and salts. You know, all these steps should be reasonably equal in size. If any one of these steps on this turbidity chart is expanded significantly, you know you have a turbidity issue. So right now, with the unit off at 0 millivolts, we've gone up to 100 millivolts with gas only. That's very good. If, for example, this first step, we're up at 500 millivolts with gas only, then we know we have contaminated gas supply. The nitrogen or the air is contaminated with moisture or hydrocarbons or mold, who knows what. And that'll cause turbidity, and it'll cause increased noise. So instead of 2 millivolts, you might be getting 6 millivolts in noise, which is abnormal. You want to see less than 2 millivolts noise, gas only at 100 millivolts. Now, we're going to turn on and add liquid to the ELSD. And this is your mobile phase coming from your HPLC. So here is our solvent line. We're connecting to the nebulizer. And we're going to turn the pump on, 1 ml a minute. And we're going to see the baseline jump a little bit. We'll see liquid coming into this glass cell, and this glass cell will start spraying and get condensate in it very shortly, provided everything is working. Yeah, here it goes. So the baseline is just spiked up to 1100 millivolts, which is up here. When you initially introduce solvent, that's pretty normal. You're going to get solvent shock. The unit's going to go full scale for a short period of time, but this should start coming down very shortly, unless my water's contaminated. Let me see where it's at. Gain 12, I am at 500 millivolts at gain 10, and it's coming down slowly but surely. So that tells me my water is pretty good. This water has been sitting here for probably about a month, so it's probably slightly turbid, which is not ideal, but this proves the point that your mobile phase can become turbid, especially water over time. It's critical to change your water almost daily. I mean, 3 days is typical for some clients, but I've had some clients with water that's a year old, and they wondered why the detector wasn't working. And they literally had fish swimming in the water. Well, no fish, but algae for sure. So now we're at gain 11. I'm at 300 millivolts. When I go to gain 12, I should be on scale now after the initial solvent shock. And this is just water without a column. So I'm at about 600 millivolts at gain 12. I'm on scale, and you can see the baseline is coming down very slowly but surely. Here is where we are now. So the water has now added, let's say, 200 millivolts here, additional. So now, at this level, we're at 300 millivolts of turbidity. And then this last step is where you add the column. And that the maximum hierarchical complexity of any HPLC system is you're operating up here at the top of the stairs. You have a column, you have mobile phase, you have gas, and your detector is running. This is where you're operating. When you call me and tell me you have a problem and you're at the top of this hierarchical chart, the first thing I'm going to tell you to do is take the column out of the system and see where your baseline is with solvent only. If you still have noise and noise issues and spiking, then I'm going to tell you to turn the solvent off and go to gas only and find at which step your detector is quiet. Once you've established the detector is quiet with gas only, but is noisy with your mobile phase is dirty. If it's still quiet with the mobile phase and you put the column in, and you have a huge step here and a lot of noise, then your column is bleeding silica. And that is a common problem with ELSDs. ELSDs see silica bleed. UV detectors do not. Your UV detector will be perfectly quiet, think everything's normal. ELSD will go off scale because of the silica bleed. All these things add up to turbidity. Dirty gas, dirty solvent, dirty column, to the point where you have no dynamic range left in the detector because your turbidity total is so high. The way you have to look at turbidity is like the depth of a lake. You could have 2-foot waves on top of a 10-foot lake, or you could have 2-foot waves, which is noise, in a mile-deep ocean. Turbidity is that depth, is the dynamic range that you're tying up with the detector. The more dynamic range you tie up with turbidity, the less response you're going to get out of the detector because there's no dynamic range left. So purity is critical at every step.